Hi everybody, welcome back to Calculus. This is going to be a video on the Superfund chart. So just to recap, the fund chart was the relationships between f prime, and f double prime, and so we had fun, concave up, concave down, f prime was increasing or decreasing, f double prime was plus or minus, and then over here, when f was increasing or decreasing, f prime was positive or negative. What the Superfund chart does is extend this to the integral of f, because again, going up on this chart we have antiderivatives, and so we also have here where most often g is defined as the integral of f. And so if we go down, that means that g prime is f, and g double prime is f prime, and g triple prime is f double prime, although that's not very much used for problems. And then, to construct the Superfund chart, we essentially take these 6 relationships and we copy and paste them here. Oops, that should just be concave up. And then once more, so that we have increasing, decreasing, plus, minus. So really there's like a concave up and a concave down up there, but we don't care about those. And then, if you can imagine, getting rid of this so that we're only looking at these relationships. So altogether, the Superfund chart looks like this. Ta-da! And it's called the Superfund chart because the integral symbol is an elongated S for summation, so it's like S and then fun or super fun? Sure. Cool. Let's give it a try and see how this applies to real-world AP problems. Alright, so here's a graph of a function f. There it is there. And it says that f is the continuous function defined on the closed interval whose graph consisting of 3 line segments and a semicircle at the origin is given above. And here is the indicator that we should probably use the Superfund chart. G is the integral of f of t dt. So just based on this, we can go ahead and set up our Superfund chart. So g, g prime, g double prime, and then we have equals the integral of f equals f equals f prime, like that, and then concave up, increasing, decreasing, concave down, plus minus, increasing, decreasing, plus minus. Great. And then there are going to be several questions associated with this, and we will use the Superfund chart for most of them. So let's go ahead and get started. Also, just to confirm, this one doesn't really matter in terms of constructing the Superfund chart. What you should pay attention to, however, is that if you have g equals, in this case, 1 to x of the integral of f of t dt, that when you take the derivative, you get g prime equals f of x, and that there's no chain rule in this case, but you might need to apply the fundamental theorem of calculus part 2 in this case, because very rarely it could be different, but it's just something to check. Alright, the first thing we're going to do is to find g of 2. Alright, well, do I have a formula for g of x? Yes, I do. It's the integral equation here. And so this basically means that I'm going to replace the x up here with a 2. So g of 2 is the integral from 1 to 2 of f of t dt. And we might have been doing a lot of integral rules with like antiderivatives and all that stuff, but in these cases, because you have a graph, remember that the integral is also the area under the graph. And so between x equals 1 and x equals 2, we have this little triangular region. And so the area of that would be a triangle, 1/2 base times height. The base of it is 1, because we're going from x equals 1 to x equals 2. And then if you notice, the slope of this is negative 1/2, which means that the y value, or the height of the triangle, is also negative 1/2. And so we have negative 1/2 there for the height, and therefore the value of this is negative 1/4. Notice that it is negative because it's below the x-axis. Cool. Let's find another area. So let's find g of negative 2. So for this, we're going to start at x equals 1. And then let's write out our formula here. So g of negative 2 equals the integral from 1 to negative 2 of f of t dt. And it is okay that these are f of t dt. You're still just using the graph. So let's go ahead and find 1 and negative 2 on the graph. Here's 1, here is negative 2, and so I really have two areas that I'm looking at, where we have this semicircular region here, and then this triangle here. So let's just go ahead and find each of those separately. So this is a semicircle, so it is 1/2 pi r squared. The radius is 1, and so it's just going to be 1/2 pi. And then we have this another triangle here. The base of it is 1, and then the height of it is 3. And so I have 1/2 times the base of 1 times the height of 3. Now, here's where things get a little bit tricky, because, we just found the area, not too bad, yeah? But you have to remember that you're integrating backwards, and that the integral still represents the signed area, as in if it's plus or minus. So normally, this area down here would be negative, but because we're going backwards, this is going to be a positive 1/2 pi, and then this triangle here normally is positive because it's above the x-axis, but because we're integrating backwards, that will make it a negative 3/2. And so our final answer here is going to be pi over 2 and then minus 3/2. Cool. Alright, let's take a look at the some things that are also interesting. So let's find g prime of negative 3. So, well, how do I find g prime? Look at the Superfund chart. Superfund. There is g prime. G prime is f. So this means that g prime of 3 is the same as f of negative 3. And what is f? It is the y values of the graph of f. So we look at the graph of f, here it is, and I look at negative 3, that's my x value, and so right there, f of negative 3 is the y value here, and that y value is 2, because it is there, or it's halfway in between 1 and 3. Cool. Similarly, g double prime of negative 3 we can find by using the Superfund chart. Oh, there's g double prime. So we would say that this is the same as f prime of negative 3, and f prime of negative 3 are it's f prime, so this is like the slope of the graph of f. Okay, so if I look at the slope here, that would be a slope of 2 over 2, which would be a positive 1. So notice here that I didn't have to actually look at the graph, or rather, I didn't have to look at the graph of g to determine what g prime and g double prime are. Instead, using the Superfund chart, we were able to figure out what to look at on the graph of f to tell us the characteristics of g. Cool. Just like with the original fun chart stuff, we can also ask the question, where is g, increasing or decreasing? And to do this, we're going to use the Superfund chart. So let's take a look. So g is increasing here on the Superfund chart, g increasing, when g prime, which is f, is positive. So let's think about why that is true. So first of all, g is the accumulation of the area under f. And so therefore, if f is positive, that means that g will be adding area. So even if g has a negative value, as long as f is positive, we're going to be adding positive area, or accumulating positive area to that quantity. So on our graph here, we're going to do increasing here in blue, and so g is increasing when f, or g prime, which are the same, are positive. So we're going to shade that in here, and there, and that's it. And then g will be decreasing where g prime, which is f, is negative. And then just like with regular fun chart stuff, we have some sentences here. So we're going to say that g is increasing on the interval -4 to -1, because those are my x values. There's -4, there's -1. Notice that I'm using open circles. And then our reasoning is because, and here's the only difference between the regular fun chart and the Superfund chart, is you have to say because g prime equals f, and then is positive. So remember back with like regular fun chart, we basically just said, f is whatever because f prime is whatever. But here, it is important that you understand and make the connection that g prime is f. And so the best way to do that is to put that in your explanation, because then that shows that you've made the connection that this graph of f relates to g because it's the derivative of g. Alright, so let's go ahead and write our sentence for g decreasing. So g looks the same, right? G is decreasing on, let's see, -1 to +1, and then union +1 to 3, and that is because g prime, which is f, is negative there. Negative there. Cool. This talk of increasing and decreasing also allows us to answer where where g has any relative maxes or mins. So let's remember how a function has a max or min. G has a max when g goes from increasing to decreasing. That means that g prime would need to go from plus to minus. Or if g has a minimum, that would be decreasing to increasing, and so that would mean g prime would have to go from negative to positive. So this is a maximum here, and then this is a minimum here. And so to tell this, well, do we have a formula for g prime? We sure do. It's f. We're going to look to see if the graph of f goes from plus to minus or minus to plus. And so do we have any of those places? Yep, we do, right here at x equals -1. So we could say that g has a relative max at x equals -1 because g prime, which is f, changes from positive to negative there. Yeah, cool. Do we have any relative minimums? No. Notice that this point here, x equals 1, is neither because f, which is g prime, does not change sign. Cool. The last thing that we did with these were points of inflection and concavity. So here we're going to be looking at g is the integral of f concave up or down, so therefore g prime, which is f, being increasing or decreasing. So here we're looking at not a positive or negative, but whether or not f is increasing. So f is increasing here, and f is decreasing here, and here, and here. So let's go ahead and answer these questions. G is concave up on, let's see where g is concave up, -4 to -2, union 0 to 1, because g prime, which is f, is increasing there. And so remember that we're using the g prime, which is f, is increasing because we have the graph of f, which is g prime. Cool, let's do concave down. So g is concave down on -2 to 0, union 1 to 3. Okay, again, be careful that you're choosing the x values for those intervals, and this is because g prime, which is f, is decreasing there. Sweet. Do we have any points of inflection? How do we tell that? We would look to see where g prime, which is f, changes from increasing to decreasing or vice versa. So on the graph, that's where we have a color change. So here we'd have a point of inflection, here we'd have a point of inflection, and there would be a third point of inflection. So let's write that here. G has points of inflection at x equals -2, 0, and 1, because g prime, which is f, changes from increasing to decreasing, and here's where we need the vice versa because it could go either way, or vice versa there. Sorry, that's very cramped, but that's not too bad. And then, of course, there's the very last thing of how do we do a tangent line. So let's say that we wanted to do the tangent line at x equals 2. So let's do the tangent line at x equals 2. So this is going to be y minus y1 equals m, x minus x1, and we're going to do the tangent line at x equals 2, the tangent line to g of x at x equals 2. So really this is going to be y minus g of 2 equals g prime of 2, x minus 2. So how do I find g prime? or sorry, g of 2, well, we kind of already did that, but to refresh, we would take 2 and plug it into the equation there, and so that would be the area, again, from 1 to 2 right there, so that's going to be a negative 1/2, so I'd have y minus, or really plus, 1/2, and then g prime of 2, remember that g prime via the Superfund chart is really f of 2, and that would be the y value here. And so, unfortunately, that also ends up being negative 1/2, so they're not necessarily the same value as the g of 2 value, but this is not too bad. And so that would be our tangent line equation, and so, again, recall that we're going to use the integral definition to find g, and then to find g prime, or the slope, we would really go back and just look at the y value of f. So hopefully this gives you a better understanding of the Superfund chart. Yeah, good luck, have fun, make good choices, yeah.